So, in the previous lecture we had seen that electric field and magnetic field, they depend on frame. What you have a pure electric field in one frame may become electric field and magnetic field in some other frame. Similarly, what is a pure magnetic field in one frame may become electric field and magnetic field in some other frame. The clue of this mixing comes from the very definition of magnetic field, where we define magnetic field using force equal to q times v cross b. So, the velocity comes into picture. So, by changing the frames we are changing the velocities, and therefore, you do expect that fields are frame dependent. Just like space and time, as long as you are one particular frame, time has its own totally different kind of identity, space has its own different kind of identity. Similarly, you have energy, momentum. So, if you change the frame, these things get mixed up. Once again, in that frame you have a separate energy, separate momentum, separate time, separate space. But then it is like you have a vector and then you are rotating the frame, you are changing your xy axis and the components are changing. So, as long as you do not change your frame, xy axis are fixed, then a vector has a definite x component, definite y component, definite z component. But once you rotate your axis, then these components change, although the vector remains the same. So, electric field and magnetic field seems to be some kind of components of a particular entity which you can call electromagnetic field. So, if you have in one frame, then the components are electric field components and magnetic field components separately. But once you change frame and try to relate the fields in one frame to the fields in other frame, then you have mixing of E and B field. So, today I will be talking of the transformation of EB components from one frame to other frame. So, let me start with frame S prime. Suppose I have a frame S prime, and in this S prime frame we have a charged particle q at rest. This is at rest. So, there could be some electric field here, some magnetic field here in this frame. Since it is at rest, magnetic field will not exert any force. You only have electric field, force due to electric field. So, force, let me write prime here, everything is prime. So, the force on this particle will be q times E prime, this is the force. So, you have Fx prime equal to q Ex prime, you have Fy prime which is q times E y prime, then Fz prime which is q times E z prime. Now, you can make transformation to S frame. So, you remember how to make this transformation? We used in the previous lecture also force transformation. Fx prime is equal to Fx minus F dot u, then V divided by 1 minus uxv by c square. Fy prime was Fy multiplied by square root 1 minus v square by c square, then the same denominator like that. And if you revert, go for inverse transformation, you change primed and unprimed quantity and v is replaced by minus v. So, you can immediately write what is Fx. Fx is Fx prime and then minus this is F prime, this is F prime and dot u prime and then v becomes minus v. So, this becomes plus here and divided by 1 plus here ux times v by c square, and fy from here, fy is equal to fy prime square root 1 minus v square by c square, and then divided by 1 plus ux v by c square prime here, that is it, and similarly fz. So, if I transform these forces here fx prime, fxy prime, fxz prime to fx, fy, fz, this u prime is 0, because I have taken my particle at rest in S prime. So, u prime is 0, and therefore, it is a great simplification. What you get is fx is equal to just fx prime, because this is 0, this is 0. So, this is fx prime, and that is q times ex prime. Then fy is equal to fy prime square root 1 minus v square by c square, because this denominator is just 1. So, it is this quantity, and what is fy prime? Fy prime is q times and then ey prime and square root of 1 minus v square by c square, and similarly fz will be q times ez prime and square root of 1 minus v square by c square. So, keep this in mind, we will be using it. Now, come to S frame. Now, come to S frame and look at the same situation. Look at the same situation from S frame. So, in S frame there will be some electric field, will be some magnetic field, and this particle will be moving in S frame with a velocity v in positive x direction. So, from S frame you have this particle q which is moving in this direction with a velocity v. This is your S frame, and you have some electric field, you have some magnetic field. So, if you have a charged particle moving in some electric and magnetic field, you can write the force from the very definition. So, F as seen from S frame will be q into E and plus q into V cross B. So, this is q E x I cap plus E y j cap plus E z k cap, it is this quantity, then plus q V is V x I cap plus V y j cap plus V z k cap, and then cross product with B, cross product with B. So, what is B then? B is B x I cap plus B y j cap plus B z k cap. But then this is 0, because your velocity v, velocity of this particle q is in x direction. So, this part is 0 and you only have this part. So, this will be equal to, and this V x is just V, right, this V. So, let me remove this from here. So, it is q and then E x I cap plus E y j cap plus E z k cap, and then plus q, then I cap cross I cap is 0, this I cap cross this I cap is 0. So, it is here V. So, V will always be there, and then B y, I cross j is k. So, k cap, then minus V will be here, q is anyway here. So, this V and this B z and j cap, minus because I cap cross k cap is minus j cap. So, this is it. So, what is Fx? What is Fx? This is F, this is the force on this particle because of the electric and magnetic field. So, Fx collect I cap, where is I cap? I cap is only here, and therefore, it is just q into Ex. So, Fx is q into Ex. Fy, this is at two places, j cap here, j cap here. So, q into Ey, and then q minus q v b z, that is it. So, this is our y component, and the z component f z is equal to q into E z, and k cap is also from two places. So, you have here and here q into v into b y. So, plus q into v into b y. So, these are the force components in S frame, but we have already obtained the components of the force in S frame using these transformation equations. This Fx, this Fy, this Fz, this is same as this Fx, this Fy and this Fz. So, you can equate them. So, if you equate them, what happens? Fx, let us equate. Fx is q times Ex prime, and here Fx is q times Ex. So, it tells me that Ex prime is same as Ex. So, Ex prime is equal to Ex. If you change frame, the component of electric field in the direction of the frame does not change. Ex prime is same as Ex. Fy, this Fy is here, q Ey prime square root 1 minus v square by c square. So, q into Ey prime square root 1 minus v square by c square. This is Fy, but Fy is here also. It is q into Ey and minus qvbz. Okay. So, I am taking Fy from here, q times Ey and minus qvbz, and I am taking Fy from here, which is q Ey prime square root 1 minus v square by c square. So, that tells me that this Ey prime is equal to, Ey prime is equal to, so I am dividing by these things, q cancels out, and what you have is this Ey here, this Ey here, Ey here, and minus vbz, so vbz, and then divided by square root 1 minus v square by c square. All right, this q cancels out, and then you have Ey prime equal to Ey minus vbz divided by this factor, and similar story for Fz. Fz is equal to q Ez prime and square root 1 minus v square by c square, and Fz here is q Ez plus vby. So, remember, it is plus here, it was minus here. So, you have q Ez prime, q Ez prime and square root of 1 minus v square by c square, and that is equal to q Ez, q times Ez, and then plus v by. So, plus v by. So, this q cancels out and you write Ez prime from here. Ez prime is equal to Ez plus v, then by, this by, and divided by square root of 1 minus v square by c square. That gives you the transformation equations for electric field. Of course, here you will have magnetic field mixing, for those components. You can do a similar analysis, little bit more mathematically involved, where you take a particle in S prime which is going in y direction, then you write what is the force here, make a transformation, and then come back here, make velocity transformation, and do similar kind of analysis to get the transformation equations for magnetic field components. And those will be Bx prime equal to Bx. So, the parallel component of magnetic field also does not change when you change frames. You are in one frame, then you are going in some other frame, inertial frame, which is moving with respect to the first frame in some direction. So, the component of electric field and magnetic field, each of these two components will remain unchanged. Bx prime is Bx, Ex prime is Ex. Then By prime. By prime will be By plus V by C square and then Ez and divided by square root 1 minus V square by C square. Slight change. Ey prime is Ey minus Vbz and By prime is By. So, it is By, and then correspondingly this Ez is there, and this minus is plus, and V becomes V by C square. Dimensionally it is necessary because E has same dimension as V into B, right. Q times E is force, Q times V cross B is force. So, electric field and velocity times magnetic field, they have the same dimensions. So, here it was E and Vb, that is fine, but here it is B here and E here. So, you multiply by V by C square to get the same dimension, so that you can add. Then Bz prime is equal to Bz and minus V by C square and Ey divided by square root 1 minus V square by C square. So, these are the transformation equations for electric field and magnetic field components. So, we will do a practice problem on this before we leave. So, let me erase all this. A parallel plate capacitor has surface charge densities plus sigma and minus sigma on the two plates. So, what you have is, you have a capacitor which has positive charges on one plate and negative charges on other plate, and the surface charge density is sigma here and minus sigma here. So, that is the first part. The capacitor moves parallel to the plate with a speed v. So, parallel to the plate. So, if this is a plate, it is parallel. So, we can say that this whole capacitor is moving with a velocity v in this direction, which we will take x direction. So, you have to find electric field and magnetic field in the capacitor. So, what we will do? If this velocity were not there, it was very simple. The electric field would have been just sigma by epsilon naught and the magnetic field 0. But it is moving with velocity v. So, there could be some magnetic field, electric field might change. So, we have to check. So, let us call it S frame and go to S prime frame. Go to S prime frame, which is moving with respect to S with this same velocity v. So, what happens there? There this capacitor is at rest. So, if I draw the picture from S prime, I have a capacitor and I have positive charges here and I have negative charges here, and then this is at rest. So, do I say that electric field is sigma over epsilon naught in this direction? You can call it y direction. So, do I say this? No. Why? it is at rest. The problem is this is moving, this is at rest, in this frame it is at rest, and charge density, surface charge density is charge per unit area. So, this sigma which is given here is charge per unit area. So, on this capacitor if you take a unit area, then or some area, then the charge contained here divided by that area will be this sigma. When you change frame, this area changes, the charge remains the same in this area, but then the area itself changes because of length contraction, right. You have length and width. So, you can take a rectangular area, and then the length which is parallel to the motion will change, length perpendicular to the motion will not change, but the area will change. And since this is at rest, the length is largest, rest length is the largest length. So, if the length here is L, length here will be more than L, L divided by square root 1 minus v square by c square, and the perpendicular length will not change. So, the area will increase because of that length contraction phenomena, the area will increase and charge is same. So, the charge density will decrease. So, you will have plus sigma prime here and minus sigma prime here, and the sigma prime will be sigma square root 1 minus v square by c square. So, the electric field here in S prime is this sigma prime divided by epsilon naught in j cap direction, and that is sigma square root 1 minus v square by c square and by epsilon naught in j cap direction. So, Ex prime is 0 and Ey prime is sigma by epsilon naught square root 1 minus v square by c square, and Ez prime is 0 in this frame, and B is 0. So, all components of B are 0, Bx prime equal to By prime equal to Bz prime equal to 0, all components of magnetic field is 0, there is no motion here. So, no question of magnetic field. So, now I can make use of the transformation equations that I have already written here to get the quantities Ex, Ey, Ez, Bx, By, Bz. So, inverse transformation is needed, right. I have the components in primed frame, S prime frame, and I want from here I want components in the S frame. So, inverse transformations are needed. I can immediately write those also, same method, interchange primed and unprimed quantities and replace V by minus V. So, what is Ex? Of course, this is Ex is equal to Ex prime. What is Ey? Ey equal to Ey prime, and plus this V becomes minus V. So, plus V Bz and then divided by square root 1 minus V square by c square, and Ez will be Ez prime, here Ez will be Ez prime and minus V By divided by square root 1 minus V square by c square, and this side Bx is Bx prime and By is By prime and minus V by c square and Ez prime divided by square root 1 minus V square by c square, and Bz will be Bz prime and plus V by c square and then Ey prime square root 1 minus V square by c square. These are the inverse transformations. So, let us start writing. Now, I am going back to S frame and writing the components Ex, which is same as Ex prime, and Ex prime here is 0 because the electric field is in this direction. So, Ex prime is 0, Ex is also 0. Then Ey. Ey is Ey prime. So what is Ey prime? Ey prime is sigma over epsilon naught square root 1 minus v square by c square. That is Ey prime plus v into bz. There is no bz. There is no bz. Prime here. Yeah, that's fine. So though no bz prime, so bz prime is 0. So this second term I don't have to write. Then divided by square root of 1 minus v square by c square, which is sigma over epsilon naught. So even if the capacitor is moving, these charges are moving, the electric field is still given by charge density sigma divided by epsilon naught. Then Ez. Ez will be Ez prime 0, By prime 0. So this will be 0. So Ez is 0. Then come to magnetic field, Bx. Bx is equal to Bx prime, and Bx prime is 0. Bx prime is 0. So Bx is also 0. What is By? What is By? By prime, that is 0, minus v by c square Ez prime. Ez prime is also 0. So Ez prime is 0 and this By prime is 0. This is 0. Bz. Bz is equal to Bz prime, which is 0. Don't know Bz prime. So it is 0. Then v by c square, and then Ey prime. Ey prime is here. Ey prime is sigma by epsilon naught square root 1 minus v square by c square. Then divided by square root 1 minus v square by c square. So this cancels out and you have Bz, which is 1 by epsilon naught c square. Do you remember what it is? 1 by epsilon naught c square, that is mu naught. So you can write this as mu naught here and then v sigma. This is our Bz. So you have an electric field and you have a magnetic field, and the magnetic field is in z direction. So if this is y, I have taken this as y and this as x, then the k direction, the z direction is coming out of the board. So if the plates are moving like this, then there is a magnetic field which is perpendicular in this direction. So that is the z direction coming out of the board. You have a magnetic field in this direction, and the value of that magnetic field is given by mu into v into sigma, mu naught into v into sigma. V into sigma is called current density for this plate as well as for this plate. If you have sigma, surface charge density, sigma, the whole thing is moving with velocity v, you have a current density that is defined as sigma times v in this situation. So you can just write it mu naught times k. So you have an electric field which is in this direction, this is the electric field, and then you have a magnetic field which is coming out here. So I can show it by dots. Remember this symbol, you have magnetic field here in this direction, and that this is sigma by epsilon naught, and this b is mu naught times k. That's it.